Hi, in this video, we shall be discussing a question taken from this particular question paper code. It's an AS A-level question paper. It's a question taken from AS A-level question paper. So let's go to the question. So here is the question. You may pause the video and read through the question. If you have not, I'll start the explanation. P, Q, and R all contains 5 carbon atoms. So here is our P, Q, and R. These are the 3 compounds. They are 5 different compounds. That doesn't mean that they are isomers. And it's clear that they are not isomers. We need not even have to count them, count the atoms, because there is nitrogen present in compound P. But Q and R doesn't have nitrogen. That clearly indicates that these are not isomers. They are just 3 separate compounds, and a student is performing several tests to identify the functional groups that are present in these 3 compounds. So a student carries out several tests to distinguish between P, Q, and R. Complete the table identifying any observations for the reaction of each reagent with P, Q, and R. If no reaction occurs, write no reaction. So here the student performs several tests, but all of them has not been included. Only the relevant ones, the ones with which the functional group in the compound gives a positive response, has been tabulated. And the student observes that with sodium with 2,4-DNPH. 2,4-DNPH is nothing but 2,4-dinitrophenyl hydrazine. And it's like you have a benzene ring. On the second position, there is an NO2 group. On the 4th position also, there is an NO2 group. And it is connected to hydrazine. Hydrazine is nothing but NH2NH2. This is hydrazine. So one of the hydrogens from one of the nitrogen has been replaced with 2,4-DNP, which is 2,4-dinitrophenyl group. So one of the hydrogens is replaced means, let's assume that the hydrogen on this has been replaced. One of the hydrogens has been replaced. So this nitrogen is left with one more hydrogen, and there is the NH2 group. So this is actually 2,4-DNPH, 2,4-dinitrophenyl hydrazine. So the student performs the test with sodium, metal, then with 2,4-DNPH, and also acidified potassium dichromate. Now, as an introduction, let's see what will be the result that will be, what are the positive outcomes that would be observed with these 3 reagents. So here I have shown an overview of the positive result with the 3 reagents the student has used. So if it is sodium in alcohol, what happens is there's a redox reaction that is happening. So let me take let me assume that the alcohol is, say, methanol. If the alcohol is methanol, what happens is when you're dropping sodium into methanol, this methanol can be splitted up as CH3CO minus, CH3O minus, and H plus. The sodium, what it does is it will be undergoing oxidation, meaning it will be losing its valence electron. So sodium is there with its valence electron. That valence electron is lost to proton. So sodium on the go becomes, sodium gets converted to Na plus, and we are having a hydrogen atom. Now, this hydrogen atom doesn't have an independent existence. So what it does is it combines with one more hydrogen, another hydrogen that will be produced from another methanol group. So we have 2 hydrogens produced from 2 methanol groups, and those 2 will combine to give a hydrogen molecule. And that hydrogen molecule is actually observed as bubbles here. These bubbles are nothing but hydrogen molecules produced by the redox reaction between the alcohol and sodium. So in this case, I can write this is giving CH3O. This is negative, this is positive. This portion of alcohol is negative, sodium is positive, negative positive will be attracted. So it will be forming a salt, and hydrogen will be the gas that is the next product that is produced. So if I'm balancing it out, 2 alcohol, 2 sodium gives 2 sodium methoxide and hydrogen gas. So this will be the balanced equation. So here is the balanced equation for the reaction between an alcohol and sodium. It's a redox reaction that produces hydrogen gas. So if an alcohol is present, and if you're dropping if the alcoholic group is present and sodium metal or potassium metal is alkali metal, sodium or potassium, both will work. So if you're dropping the alkali metal into it, definitely it will be producing hydrogen gas. So that's the test with sodium metal. Moving on to the next test, which is 2,4-DNPH. 2,4-DNP or 2,4-DNPH. In some cases, we write H, 2,4-DNPH. In sometimes we omit that H and simply write it as 2,4-DNP. Both are absolutely fine. So it's 2,4-dinitrophenylhydrazine test. So this reagent, 2,4-dinitrophenylhydrazine, is having an orange color. This is it, or it looks like this. To this compound, if an aldehyde or a ketone, I'll highlight, it's an aldehyde or a ketone. If you're adding it into 2,4-dinitrophenylhydrazine, it gives an orange precipitate. I'll repeat once again. Into 2,4-dinitrophenylhydrazine, if an aldehyde or a ketone, aldehyde or a ketone, if you're adding it into 2,4-dinitrophenylhydrazine, which is orange solution, that will be giving an orange precipitate. So that's how we will be identifying the presence of either an aldehyde or a ketone. So if the alcohol is present, definitely don't expect this particular reaction. So I hope the 2,4-dinitrophenylhydrazine test is clear. Yeah, so now let's move on to the next one. It's acidified potassium dichromate. As far as acidified potassium dichromate is concerned, it's an oxidizing agent. It can oxidize either an alcohol or an aldehyde into carboxylic acid. Alcohol will be converted to first an aldehyde followed by carboxylic acid. It will be the aldehyde which is formed will be immediately getting oxidized to carboxylic acid. So obviously if there is an aldehyde, that also will be for sure converted to carboxylic acid. And because of this redox reaction that happens with an aldehyde or an alcohol, the solution turns green. But if it is a ketone, ketones cannot be oxidized to carboxylic acid. This oxidation doesn't happen. So with ketone, we will not see a green color. So I hope the outline of the 3 tests are clear. For further reference, I'll just show you the textbook pages also in case if you want to refer the textbook. So in this particular textbook, on page number 228, this is 228. On page number 228 of this particular textbook, we have the reaction for alcohol and sodium. The reaction between alcohol and sodium has been mentioned in page number 228 of this particular textbook. For the other 2 reactions, in the same textbook, page number 231 gives the acidified dichromate, potassium dichromate test. So this is the acidified potassium dichromate test. And for the 2,4-DNPH test, it is mentioned on page 238. This is for extra reference if you want to go through the textbook. So yeah, now let's go back to the question. So P, Q, and R, if you're making it react with sodium, as I highlighted before, sodium is a reagent which is going to attack only alcoholic group. If there is an alcohol, hydrogen gas will be produced. If you're comparing P, Q, and R, we can find that alcoholic OH group is present only in P. It's not present in Q, it's not present in R. OH is not present in Q and R. So neither Q nor R is going to give you a result. It's not going. P alone is going to give a positive result. Q and R doesn't respond to the first test. So here there is effervescence. Hydrogen gas is evolved. Hydrogen gas. Observation would be evolution of gas, or I can write effervescence. Effervescence that's what is observed. Bubbles will be seen, and observation with Q and R, the reaction itself doesn't happen. So there is a no reaction. There is no reaction here. There is a no reaction here. Moving on to the next one, it's 2,4-DNPH. It's 2,4-dinitrophenylhydrazine. As I highlighted before, 2,4-DNPH is going to react or respond positively only to aldehydes and ketones. And if you're observing P, Q, and R, P doesn't have an aldehyde or a ketone group, but Q does have one. Here we have a ketone. There is a ketone out here, and this is an aldehyde. Here we have an aldehyde. So definitely ketones and aldehydes which give an orange precipitate. So definitely Q and R, which contains the ketone and aldehydic functional group, is going to respond positively. They are going to give an orange precipitate. Only P does not give an output. So here I can write orange precipitate. Orange precipitate. Here also we are going to see an orange precipitate. Now with acidified potassium dichromate. Now let's see what happens with acidified potassium dichromate. Now, if you can remember, I'd said that acidified potassium dichromate will be oxidizing alcohols as well as aldehyde, but doesn't oxidize ketone. So now you might be wondering, like both P and R will be oxidized. Q, of course, doesn't get oxidized because it's having a ketone. So there's no question of Q getting oxidized. There's no confusion there. But coming to P and R, this is an alcohol, this is an aldehyde. So we expect both P and R to be oxidized by the acidified potassium dichromate. And here it is clearly stated that there is a no reaction with P. So now there is a puzzle here. The thing is, P is having a tertiary. This is a tertiary carbon, and this is a tertiary alcohol. As far as oxidation of aldehyde is concerned, primary will be oxidized to aldehyde, further gets oxidized to carboxylic acid. I indicated there, aldehyde, alcohol to aldehyde, further to carboxylic acid. Aldehyde can be formed only from primary. So primary can respond to this test positively. If it is secondary, this can be oxidized to a ketone. Ketone will be definitely formed. So if secondary alcohol is there, because of the formation of ketone, there will be a noticeable color change. Orange will be turning to green. So that also responds positively. It's just that ketone further doesn't get oxidized, but still, because the secondary alcohol is getting oxidized to ketone, obviously we will see an orange color changing to green. But when it comes to tertiary alcohol, it doesn't get oxidized. As long as it doesn't get oxidized, we cannot expect the orange color to change to green. So that is the reason why, because P is a tertiary alcohol. P doesn't get oxidized. So there is a no reaction. Orange color is a not formed. Q also, there is a no reaction. But as far as R is concerned, here there is an aldehyde. This aldehyde will be converted to carboxylic acid. So this do give a color change. The orange color will be changing to green. So the observation will be green for molecule R. And here we have the marking scheme. This is the marking scheme for what we discussed just now. So now let's move on to the next part of the same question. Q is reduced by sodium borohydride. I've put the structure of Q here. And sodium borohydride, actually, it's a reducing agent which can reduce carbonyls. Reduction of carbonyls. It can be aldehyde, it can be ketone. Aldehydes or ketones will be reduced to alcohols. So if you're having, I'll just give an explanation to that thing. Here is the explanation for that change. So if you're having a primary alcohol, that can be oxidized to. Oxidized means addition of oxygen. It can be oxidized to an aldehyde. And further, it can be, if you're adding an oxygen, if you're adding more oxygen, it will be further converted to carboxylic acid. As an example, if you want, I can take ethanol, CH3CH2OH. So this gets oxidized. Oxidation means addition of oxygen, removal of hydrogen. So this OH functional groups get converted to aldehyde. So this portion, you can replace it as CHO. That portion becomes CHO. Further, if you're oxidizing it, what happens is this aldehyde gets converted to carboxylic acid. So how can I write? CH3 remains the same, there's no change, but only the CHO changes to COOH. This is the oxidation conversion. Obviously, if you're carrying out a reduction means you're doing the opposite. Reduction is addition of hydrogen or removal of oxygen. So if this is oxidation, so now let's see what happens during a reduction. So as far as a reduction is concerned, it is addition of hydrogen, removal of oxygen. So when that happens, carboxylic acid, if you're adding hydrogen to its addition of hydrogen, if hydrogen is added to carboxylic acid, that gets converted to aldehyde. And if the aldehyde is further reduced, if the aldehyde is further reduced, you get a primary alcohol. So it's a reverse process, reverse thing. Oxidation, primary alcohol to carboxylic acid. Reduction, exactly opposite, carboxylic acid to primary alcohol. So example, if carboxylic acid, let's take this above molecule itself, ethanoic acid. So when I'm adding hydrogen, I'm actually increasing the hydrogen number, decreasing the oxygen. It becomes aldehyde, and like before, only the carboxylic acid portion undergoes the change. The rest of the molecule remains unchanged. So CH3 remains as it is. Only COOH, I need to replace it with a CHO group. Further, if it is reduced aldehyde, we are in the CHO group, we are increasing the number of hydrogen. So that becomes CH3. Previously, only one hydrogen was there. Now it becomes CH2OH, addition of hydrogen. So reduction oxidation is the reverse thing. Okay, this is regarding primary alcohol. Let's go for secondary alcohol also. Now let's see oxidation. Now let's see oxidation. As far as oxidation is concerned, okay, let's go for a secondary alcohol. As far as secondary alcohol is concerned, when it is subjected to oxidation, oxidation is addition of oxygen. So secondary alcohol takes up an oxygen to give a ketone. So what happens? I can write CH3, CHOH, CH3. So secondary alcohol will be connected to two other carbon atoms. When it is oxidized, what happens is, when it is oxidized, what happens is this hydrogen and this hydrogen will be removed, and we end up with CH3, C double bond O CH3, a ketone. But the thing is, further oxidation to carboxylic acid is not feasible because carboxylic acid is a terminal functional group having C double bond O connected to an OH. It has to be connected to an oxygen and followed by hydrogen. In ketone, just because the carbonyl carbon is connected to two other carbon atoms, having an OH is impossible. So ketone further doesn't get oxidized to carboxylic acid under normal conditions. Okay, so if this is oxidation, let's see how reduction works. For reduction, it's the opposite. So if I'm having a ketone, when I'm reducing it, when I introduce hydrogen into it, I get the secondary alcohol. Secondary alcohol. So taking the same above example, CH3, C double bond O CH3, what happens is, this carbon and this oxygen will be taking up two hydrogens. This pi bond will be cleaved and it becomes a single bond. And the product would be CH3, C, O. This takes up a hydrogen. This also takes up a hydrogen and CH3. So we get back the secondary alcohol. Going back to our question, Q is reduced by sodium borohydride. Q is reduced by sodium borohydride means its carbonyl functional group, the ketone which is present, will be getting reduced to the respective alcohol. So if the carbonyl is getting reduced, just as we saw just now, just as we saw, hydrogen gets added, this double bond will be broken, it gets added here, it gets added here. So the product is CH3, COH, H, CH2, CH2, CH3. The rest of the molecule remains the same. Two extra hydrogens are added. So this will be C5 hydrogen. Previously there was 10. In this there were 10 hydrogen. Two more are added here. So this will be 12. Oxygen number doesn't change, O. So here I can write C5H10O. Instead of reducing agent sodium borohydride, writing the whole sodium borohydride as such, question clearly indicates that we can use H. We can represent the reagent with H. So H gives C5H12O. So when it becomes when we are balancing it, we have to include 2H. So this is the reaction that was expected. Let's take the marking scheme. See, this is it. Now going to the next part of the question. C part. R exists as a pair of stereoisomers. Identify the type of stereoisomerism shown by R and draw the structure of other stereoisomer. Draw the structure of other stereoisomer. Now, what are stereoisomers? There is stereoisomer, there is structural isomer. So actually, as far as stereoisomers are concerned, here, atom to atom connections remains the same, meaning all the bonds, the CH bond, or the CC bond, everything remains the same. Then what is the difference? But orientation of groups, positioning of the groups, it can be the positioning of CH3, it can be the positioning of hydrogen, it can be the positioning of CHO. Orientation of groups differ. Groups differ. So this is how differ. This is about a stereoisomer. In this molecule, there is a double bond. Always, as far as a double bond is concerned, there will be restricted rotation. Normally, if there is a single bond, there will be a rotation around the CC bond. But when it comes to a double bond, the double bond doesn't permit complete rotation of the CC bond, meaning that portion, just because the rotation is restricted, this position of hydrogen, just because there is restricted rotation around the CC double bond, these two hydrogens will be opposite, always opposite in this molecule. They never come close together. And as far as these two are concerned, they also remain opposite to each other. They cannot come close to each other. So this is one isomer. I can have its another isomer where instead of having these two hydrogens opposite, in the next molecule, in the isomeric molecule, I can have them together. I can have them together in the sense, I can have them on the same side. So C double bond C have both the hydrogens together. Obviously, the CHO group and the CH2, CH3 group will be on same side. These two isomers are called geometrical isomers. So type of isomerism is geometrical. And the stereoisomer of R, this is the stereoisomer of R. This is the stereoisomer of R. Here, this is the answer as per the marking scheme. Now let's move on. Here we have the last part of this particular question paper. You can pause the video and read through the question. The IR spectrum shown corresponds to one of P, Q, and R. It's not for all the molecules. It's just one molecule alone. It might be R, it might be Q, it might be P. We don't know whether it is belonging to P, Q, or R. Did use which of the following compounds, P, Q, or R, produces this spectrum? Explain your reasoning. Now we have to figure out whether this spectrum belongs to P, Q, or R. Now, how will you identify it? You can see here, as far as this spectrum is concerned, you can see so many peaks in the, as far as the spectrum is concerned, so many peaks have been shown. But always keep in mind, the peaks below 1500, the peaks in this region, it is actually known as the fingerprint region. Fingerprint region means it is like unique to a particular molecule, just like we have our own fingerprints. X and Y have their own fingerprints, but they will never match. Every individual has their own fingerprints that matches with none other fingerprints, isn't it? Likewise, that portion of the molecule, if P is giving the peaks in the region below 1500, below 1500 is the fingerprint region. So if we are taking the IR spectrum for compound P, it gives a peak which will be unique to itself. It will never match with the peak of Q, or it never matches with the peaks in R. But likewise, considering the IR spectrum for Q below 1500, none of the peaks will be comparable with that of Q or R or with any other molecule. They are unique to the respective molecule or the compound. So as far as our question is concerned, the peaks below 1500 can be completely omitted out. It's of no significance, because unless otherwise we have the real peak, unless otherwise we have an actual peak of Q or P or R, we cannot use that portion to compare and say whether it is whether our unknown substance is P, Q, or R. Forget about the peaks below 1500. We just need to focus on the peaks above 1500. So now above 1500, we have only 3 peaks. One somewhere around, this is 3000, this is 4000. So this would be, this point would be 3500. So I can, this would be 3500, this would be 3400. So somewhere between 3500, 3400, we have a very strong peak. This is a strong peak. Now there is another peak somewhere. So this is 3000, just above, just after 3000. This is 3100. Here we have 3100. Between 3000, 3100, we have another very strong peak. It's not broad. This is a very broad one, but the next one is not a broad one. We have a, but it's a really strong one. We have a very strong peak. So there's one peak, there's a next peak, and we have a third one here. So if this is 2000, this is 3000. This would be 2500. So somewhere here we have 2250. We have a peak around. So which are the 3 peaks that we are having? So let me take this as in between 3500, 3400, or in that range. The next one around 3100, 3000 range. And the third one around 2250, 3 peaks. So on an average, I'm just putting it first peak at 3400, second peak at 3100, and the third peak at 2250. Now we have got the peaks value. We have values ready with us. Now let's go to the IR table, compare these values with the table, and let's figure out which are the functional groups. So here we have the table. Yeah. Now let's compare the data, what we have got with the table. And here is the list of the data of what we had discussed before. There is one at 3400, there is one at 3100, another at 2250. Now going to the molecules P, Q, and R, there is OH, this is one functional group. There is CN bond, there is OH bond, there is CN bond, there is CC bond, there is CC bond, and here and all we have the CH bond as well. Now coming to Q, CC bond is there, C double bond O carbonyl bond is there, then of course CH bond is also there. Coming here we have again a C double bond O, this is a carbonyl, C double bond O is there. Then we have a C double bond C, and we have a CH bond on the C double bond C and a CH bond on a singly bonded carbon atom. So what are the functional groups? We have the OH. What are the bonds? OH bond is there, CN bond is there, CH bond is there. Carbonyl, C double bond O, CH. Here also carbonyl, C double bond, CH. So now let's compare the data what we have got. 3400. 3400 will be corresponding to C. It will be corresponding to an alcoholic OH. So this will be, so our first peak is because of the OH bond. We have something around 3100. 3100 is somewhere here. And it's showing that it is this, it's a carbon hydrogen bond on a doubly bonded carbon atom. And if it is a normal thing, it will be very close to it, 2800 or 2950, very close to 3000. Or so I can write this 3101. It can be because of a CH on a double bonded carbon atom, or very close to it, we have another CH bond also, but only thing this is a carbon which is having a single bond on it. Fine, okay. Then we have something around 2250 here. It corresponds to C triple bond N, or the cyanide or the nitrile group. So OH, CN and CH bond, it's present on compound P. So this peak, this IR spectrum. So this IR spectrum, what we have is actually corresponding to compound Q. It's not. So the IR spectrum we have is corresponding to molecule P, not to Q or R. So it's compound P. Now, how will we have the explanation? So we can write the 3400 centimeter inverse peak. This will be because of the OH bond. Then we have something around 3000 or 3100 centimeter inverse. So that corresponds to the CH bond. That corresponds to the CH bond. And then we have something around 2250 centimeter inverse that corresponds to the CN bond. So that's it. Let's check the marking scheme. Here it is. CN, 2250, compound is P. Then between 3100 to 3700, there is the OH peak. And they have not mentioned about the CH bond. Okay, it's fine. Thank you.